Okay, guys, let's start. Hello. Posso começar depois, vocês desculpem? Okay, good morning again. Before we switch off the lights, I have a few things to tell you. I'll try to remove a few slides just to don't run too much against time. And yesterday, I was showing you some problems that we have with a constant pH method, especially convergence, if you put more details. And today, I'm going to move to something more specifically that's more closer to what exactly we are doing in the lab. So I'm going to introduce you the kind of simplified models that we have been developing over the years. And at the same time, I'll try to apply these models and show you peculiar phenomena that you can have when you combine electrostatic interactions with some specific things in the system. So the combination of the pH, temperature, the size of your system, the charge of the control ions, these kind of things can give rise to some specific phenomena that they are in some way against your common sense. And this is what I would like to bring to discussion as well. And depending on the time, I'm trying to show also some more specific applications. So let's see how we go in time. Before I start, I also like to apologize because I'm going to be jumping a few slides. I'm probably going to follow the same strategy that Hawk used yesterday to keep the slides so you can read this slide later, but I'm not going to be discussing them in a more deep details just to avoid us to go too much against the time, okay? But you're welcome to make questions either now, during the break, or even before lunch. Or if you prefer, you can also email me afterwards, okay? So trying to visualize in a historical perspective the kind of model that we have been developing, we start with something that we call more colloidal-like models to describe electrostatic properties. So in some sense, this was a continuation of the Thunford-Kirkwood model. You can see that I have a protein here in atomic details, but I start introducing explicitly contra ions and explicitly add salts on my system. Everything is confined in a kind of a spherical box, so I can define a radius and automatically let me define the protein concentration. So this is a way that I can introduce easily in the system the protein concentration. So after this model, and also coupling this model, as you can see here, with a proton box, we start doing the very basic constant pH simulations. So here we had something that was a constant charge system. We had to specify the charge, and they remain constant during the simulation, as most of the applications are still done nowadays by many groups. But at this stage, we start introducing a proton box, and using this kind of Hamiltonian here, we could also put, again, in a phenomenological way, the pH effect. So you can see that I have a chemical contribution here for protonation or deprotonation. You can see this plus and minus over there. So as I showed yesterday, we need to plug the pH and the pKa of the different table groups. And in a Monte Carlo analysis, we are going to decide if that protonation or deprotonation process can happen or not. Okay? The evolution of this was to replace the explicit ions by implicit methods. And the reason for this was to save CPU time, so we could study this, we could apply this for protein-protein interactions. One problem that we had with this kind of model was that all the time that you were trying to move two proteins closer to each other, the acceptance rate was really very small, because if you have explicit ions, at some point you're going to have overlap between particles, which means that your rejection is going to be very high. The chance to reject a particle is going to increase, especially if you put lots of salt in the system. So this was forcing us to run long and long and long simulations for nothing, because we're not getting free energies like I said yesterday that I would like to get. So this is the reason that we have it simplified. And it's turning out that this kind of simplification actually improved the model. I'm going to show you results about this. This is the kind of model that was a side model of this initial idea for protein-protein interactions, or even protein-RNA or protein-DNA interaction as well. The continuation of this story here was to couple this titration scheme that you can see here with molecular dynamics, and that's what I mentioned yesterday that we call it the OPEP6. So we could improve the results, and also we start to be able to describe both the electrostatic part and the conformational changes and everything coupled to each other. So as a function of pH, I can change the conformation of my proteins. And the conformation of my proteins are also going to affect the electrostatics. So this is done in a more proper way. Okay, I already mentioned a few things, but let me highlight a few details here. You can see that we are working all the time on the continued description. So I don't have a explicit water model. We replace the water model by the main behavior of water. So essentially what you are doing is to screen the electrostatics by dielectric constants. And in this model, most of the time, if I don't say anything, it's going to be a uniform dielectric constant. So as we were discussing also yesterday, the dielectric interface can be useful to calibrate the results in some sense. I mean, that you can have, you can adjust this parameter to reproduce better a quantity. But in terms of physics, you can see that any number that you plug is going to provide you a result. So it becomes not really, don't have really a good criterion to do this. So if you can replace and use a uniform description, you reduce in the number of input parameters, so you simplify the things, and it can be better. We also have models, as I wrote here, model 2, that I can introduce a polyelectrolyte in the system, or a polyampholite. I have an example here. And we also use, as you can see also, this simplification. Like our polyelectrolyte is a collection of charged objects connected by harmonic springs. So this is very simple, but it's enough to capture most of the mechanism, if you'd like, especially to rationalize complex systems. So 2 models. So this is what I call our approximations. Again, the titration group, if you have a protonation, either just for the protein, or if I have a protein polyelectrolyte, whatever we have in the system, we couple with this proton box, and we can get one charge from the protein, put in the solution, and vice versa, following these rules. So this was the model with explicit ions. That's the beginning. Later, as I said, we'd like to simplify the things, and we'd like to speed up the calculations, especially to put this on the large context. So one reason, of course, is that we'd like to repeat the calculation for many different input conditions, either experimental conditions, mutations, and the other, as I said, also is to see the protein-protein interactions. So then we come up with this model. Here's the Hamiltonian. I have slides to show how we come up with these things. I'm briefly going to mention to you, but as I said, not time to go to the details. The idea started with what we saw in terms of basic physical chemistry. We started with the definition of the equilibrium constants. That's the same slide. And manipulating these equations, you can see that we can rewrite the things in a way that I can define the pKa, pH, the log of the prefactors here of your activity coefficient, the concentration. So when you rewrite things and start to manipulate, jumping a few slides, you can end up in a kind of free energy rule for the protonation using these terms. So at the end, what we get is that the free energy is going to depend on the change of your Coulomb interactions plus this chemical contribution. That's exactly the same idea that I already mentioned when I was discussing these things. So this is the way, in a very, let's say, fast version, to explain how we come up with this equation. And this part, in this version that we have, the implicit salt description, we have used the ideas from the Thunford-Kirkwood model. So the same model that I showed you yesterday, we have invoked a few extra simplifications, and we put for this internal energy, or the direct electrostatic interactions, we have used the Thunford idea, and then if you manipulate the equations, you end up in this final Hamiltonian. So you can see that salt is present here through this kappa. This is the Bi-Hooke constant. That happens also in our model to be a modified version. It's not exactly the same one that I showed you yesterday, because we also introduced in this guy the effect of the concentration of the contraions. And this number is going to be changed during the simulation depending how is your protonation. So we keep the system neutral. This is really important. The system has to be neutral, and the way to control the neutrality is through this kappa. Okay, just to give an idea about comparisons, this is exactly the first result that we got. So we had the split ion model, and then we had this one that's a simplified version. So we started comparing both because we'd like to guarantee that they could provide equivalent results. Here I have plots of charge as a function of pH, a parameter that's a charge fluctuation as a function of pH, and dipole moments of 3 different proteins. You can see that some proteins are more spherical-like objects. This one is a little bit more elongated. This is lactoferrin, one of the milk whey proteins. When I look at the plots here, all the time I'm not sure if the points are the implicit model or the explicit one, because you can see that they are on the top of each other. It's very hard to make a difference between the two models. So we could gain 2 orders of magnitude in terms of the CPU time, and we got the same results. So that's the reason that we started calling this fast proton titration scheme, because we could gain 100 times more speed just making this change. And as you can see, it's really hard to make a difference between the results, especially for the titration charge as a function of the pH. The dashed line here, the black one, is the ideal condition. It's the one that we don't use the 3D structure. The different colors, they mean different salt concentration. And as I mentioned on Tuesday, as much as we increase the salt, we start to approach the ideal behavior. So both models also respond in terms of this basic physical knowledge. We can see some slight difference, especially for the dipole moment for the more elongated molecule. So here you can see that there is you can see some small difference between the plots. Maybe for this blue one here is where you have more effects. But even so, dipole interactions usually they are not like 1 divided by R. They are more a short range. So it's not going to affect too much the results, and the difference is not that big in this case. But okay, we were happy, and we decided to make some extra tests. One test that we have done, just to continue the test, was to take several proteins and calculate isoelectric points. You can see that the experimental data between parentheses here is a little bit scattered. The reason for this is because people are measuring this under different physical-chemical conditions. Sometimes in the experimental papers, it's not even clear what was the experimental conditions. So you can see that the numbers can vary quite a lot. But our numbers were all the time closer to the experimental data. So for isoelectric points, it's not a big deal to reproduce, but at least it's a kind of, let's say, preliminary step to guarantee that your model is working fine. Okay? So here is the comparison. The next step was to start to benchmark pKa's. So we took the most used proteins for this purpose. And we have the experimental data. Here you can see 3 different proteins, the experimental data, the generalized Born approximation, all atom simulation, and our rigid and implicit model. It's surprisingly good. Come on, this was really very exciting, because we have something very fast that's able to reproduce even better things that people were running very detailed simulations. Actually, we couldn't believe that it was so good. That's why we started trying many more proteins, because it was so good to be true. Just look here. The average absolute deviations is 0.5, is equivalent to the generalized Born approach. But it's better than the atomistic simulations. Of course, when you start thinking about it, it makes sense. Because as I showed yesterday, it's very time-consuming to have a convergency when you have all these details. So you need to run really long enough to get to convergence. And these simulations were pretty short, 10 nanoseconds. So you are putting more details, but you're not able to pay the CPU price for this condition. So using a simplified model could provide us reasonable numbers. I'm not going to show you all the results, but at least I'm going to select a few things that are interesting so we can have a discussion. This guy here, this glutamate acid at position 35 of lysozyme, seems to be critical for all approaches. You can see that all the models, they have trouble to reproduce this guy. The experimental number is 6.1, and no model can come closer to this guy, including ours. But we are not really so different from the predictions from this guy. So again, we have the same trouble that anybody else has. It's not going to improve, but it's not going to be too much different than physics. That's another good thing. I'm trying to highlight the comparison of different models. So I compared more here with the 3 methods, as you can see, the GB and the all-atom simulation. I also took other protein that Benoit Roy has used his model to compare. And in this case, it's even better. Of course, depending on the system, maybe it's not going to be that good. In others, can be much better. But in general, this is the trend. We are able to reproduce much better the pKa shifts when you compare to experimental data using this very simplified model. For instance, these simulations, they are very expensive. And you can see that both the maximum deviation and our average numbers are way better. So the problem with more detailed methods is, again, the convergence. Let me give you the microphone to you. Otherwise, it would be harder to hear you.
For the ones that you had more trouble matching, do you know, are there common properties between those? Like, would you be able to predict which ones are more difficult to predict?
Yeah, we can see that this one seems to be very difficult for everybody. And I think most of the time when we have these kind of situations are for amino acids that are deep inside the protein structure. Because behind the model, there are some assumptions. So we are using a phenomenological description of the pH. And we are assuming that the change is much more related to the change in the electrostatic environment than anything else. But in real life, we know that the solvation shell is also going to be different. So when I compare the property of an amino acid that's closer to the surface, and then someone that's really very deep inside the protein structure, at the very core, the central part of the protein, the solvation environment is totally different. And we're assuming that they are the same. So all the models, they have this in common. So this might be the reason. Okay? But it's harder to test. Well, just a few examples about the titration plots. But I would like to highlight a good comparison. I mean, I was comparing a few cases, but then we decided to put everything together in a picture that we can make a comparison also with empirical methods. Empirical methods, they're way fast. They're very much used for people to start constant charge simulations. So when you are doing your input file, you use methods like PropPKa. You can see here the comparison between PropPKa and experimental data. Each of these points corresponds to one experimental point from different proteins. And here you can see the same correlation, our data, our model, and experimental data. It turns out to be very good. I mean, we have, if you make a comparison between the linear coefficient and the slopes, we have something that's 0.68. PropPKa gives you 0.51. So we are slightly better than PropPKa. We're not as fast as PropPKa, but at least we can have results that are not far from PropPKa that has a good reputation to be a good pKa predictor, especially under conditions similar to the data that they have inside their database, the training sets. Another good point is if you compare with Poisson-Boltzmann methods that are way fast than molecular dynamic simulation methods. Because if you remember, the method from Antonio Batista, he couples MED with a Poisson-Boltzmann solver. So it's good to know how is the performance. I took a larger protein here, and you can see that we are order of magnitudes fast in equivalent computers compared to the Poisson-Boltzmann solver. So these results were very promising. And it was after this data that we start thinking about, oh, come on, if they are coupling the molecular dynamic simulation with Poisson-Boltzmann solver, we can do the same. But instead of using the Poisson-Boltzmann solver, we can replace the solver by our methods. And doing so, we are going to gain the possibility to repeat the calculation much more often. So the convergence is not going to be an issue any longer. We have also extended the model for RNA. As you can see here, the results are more or less the same. I mean, we're doing at least equivalently good to others, sometimes even better than the all-atom simulations. We checked if these results could make sense. So part of our research line is to study the physics of a virus, which it seems to be very appropriate at this moment. So just to show you some results with dengue, that's a Brazilian problem, we took 2 structures that were available on PDB, and would you like to check if the titration results could be used to predict the solvation free energies. And they were making sense when you compare the experiment. So we know that this specific structure here is more stable at pH of 8.5. And you know that this other structure here, the post-fusion one, is more stable at 7. So the idea is, if I do the calculation for all the pH, for all these proteins, I should see that the minimum is going to be in different positions. And in fact, it turns out when we compare these things, you can see here the black plot is the one that's supposed to be more stable at pH 7. And in fact, it is more stable at pH 7. The other one, there is an inversion here. This one should be more stable at pH 8.7 and 8.5. And we have it here at 8.5 as more stable. So we can capture these kind of things. Why I'm showing you these results? Well, I'm telling you that we like to make the coupling between a rigid titration scheme with a molecular dynamics. So we needed to be sure that the titration scheme is able to respond well to conformational changes. So this is one initial way to show at least that we have something in this direction. So at least we can capture things. Of course, we have more results. Don't have time to show you all, but I think this is very representative and also interesting to start discussing the topic. I mean, that you can apply this basic physics or basic physical chemical description to study complex systems as virus. I mentioned the convergence, and yes?
On the slide before, I mean, can you explain why? I mean, just by looking at the free energy, I would think that 6 and maybe 9 point something would be more stable. Why?
Yeah, okay, you mean why we're not looking to this point? Yeah, okay. The reason is, here we are performing the calculation of salt like 150 millimolar. And when they do the crystallization studies to get this structure, they put other salt concentration, they put other chemicals in the system. So eventually you can get a crystal under this condition, but they are more stable in a different condition. Okay? So the point here is, okay, assuming that I'm comparing the same condition, how should it be that comparison? Of course, this is a good comment. In fact, these structures, they are going to be much more stable in a low pH. And if you remember, the virus, they like to be operational in low pH conditions. Okay? But in terms of, I mean, to compare with the experimental data that's available, we need to really make the comparison the same pH. That's why I have put these dashed lines here, just to remember that at this point. Yeah, but it's a good comment. I mean, you can see that they are more stable at this pH in nature. Okay? And also, you can see that it's important to have pH as a trigger for most of the process. So we know that it's due to the change of the pH that you start to have the infection process, or it helps a lot at least. And this seems to be general for most of the virus, by the way. Okay, I was mentioning the convergency, and you can see that we don't have a convergency problem. I mean, they converge pretty quickly. I mean, here you have the charges as a function of the number of Monte Carlo steps. In usually typical 10 to the power 4, we already have a convergence for most of the charge, even for more complex systems, bigger systems with several titratable groups. In terms of CPU time, essentially we have no cost, I mean, to work up to this point, okay? And come on, I already showed you the comparison between Poisson both. This gives you a feeling to you how quick it can be these calculations. Well, the results were good, but you can see that there is still room to improve. And furthermore, would you like to be able to compare conformational change with experiments? So we continue this job, and as I said, instead of using MID like Antonio Batista is using, we replace this one by our scheme. And for the force field, we could do this in principle for any force field. But we do the electrostatic calculations in the continued description. So we have this implicit model for solvent. We start to look around for models for force fields that would also use the same description. And there is a very nice one that's called OPEP. OPEP is a force field that has been developed to study amyloid proteins that people have been using for proteins where they like to study protein folding. And it has been developed in such a way that's very robust to reproduce several properties of the system. So it was very, very interesting. Furthermore, these guys, they already have implemented ion pairs in the model. So there is one version of OPEP that was called OPEP 5 that together with the traditional force field, they have introduced explicitly ion pairs. And when you use the ion pairs, it becomes easier for the implementation point of view to couple with the titration scheme. Because essentially, when I get the reply from my titration code, I have essentially to either turn on or turn off the ion pairs, depending if the system is protonated or not. So the implementation starts to be faster. We started, I mean, here you can have some snapshots measuring separation distance from key points in proteins. So we could compare the conformational changes for different pH, as a function of pH, and compare this with experimental data. And we can see that there is really a trend to expand or to collapse the polypeptide chain as a function of pH, in the same way that you can observe in the experiments. I have a result to show you about this later. But the first thing that we have done was, again, to repeat the same pKa calculations for all the systems that we have studied before, and including some new systems, because on the meantime, between the two papers, more research labs start to work in developing other kinds of constant pH methods. So we had to redo calculations for new methods. Some labs even were not including all the titration groups. So we had to do the calculations using all titratable groups, plus additional calculations where we remove some titratable groups because they didn't include in their study. But at the end, you can see that our comparison were good, but it was, I mean, they didn't work in the direction that we were expecting, because we expected that the combination of titration and conformational change would improve the pKas. In some cases, you can see that if I compare my rigid model, actually, it's going in the opposite direction. So it's not like very clear that for all the systems, this is going to be an improvement. Why? Well, because some proteins, they don't change too much the conformation if you have a change in pH. So for some systems, this is not going to be always true. So pKas are good descriptors to benchmark the model. Reasonable, yes, but it's not, I mean, they're not describing the whole thing. Because if the conformational change is small, a rigid model can do a good job. And this can be another reason why the other models were giving difficult results. So you combine the two effects. You combine the problem that you don't have too large conformational deviations, plus you don't have a convergence. For instance, if I compare an all-atom simulation, their maximum deviation was 1.2. We got 0.9 and 0.7 here. Slightly better, but it's not like closer, I mean, much closer to 0. There are other cases that the things were better. Just an example about the convergence, you can see that in 20 nanoseconds, even less, like here, 15, we already have a convergence. So convergence is not an issue any longer. We can run shorter simulations. I mean, just look here, that around this number, we already have a good convergence for several protonation states. So it was already an improvement, but not really something that is done completely and we can forget. We are still working to improve this later, further. But I mentioned you something that was very important. With the rigid model, we can't describe conformational pH effects on conformational changes. But with this new model, we can. And we took insulin. Insulin, you have a crystal data between pH 7 and 11. So you go to PDB, you have 4 different PDBs for different pH conditions. We can start with any of them. We can run the constant pH simulations using OPEP6. This is one that has the coupling. And we can see how is the separation distance between the amino acids. And for instance, we know that at pH 7, we should have a tendency to have what they call an open state. There is 70% of chance to have an open state. And then when you go, for instance, to pH 10, it should be closer. So if you think about separation distance, the separation distance between these two amino acids should be larger here than is there. And that's what we get when you make the comparison between how these amino acids were changed their separation distance. So for the first time, it's possible to describe conformational changes closer to the experimental data. Okay, I already talked a little bit about models. I talked actually in the first class much more about simulations and these kind of things. So now I'd like to go a little bit more to the physics side. And at the very beginning, I mentioned to you that electrostatic interactions usually is something that people say, come on, do you work with the Coulomb law? So you are in the basic school. And then I come to a question, oh, is it really so simple? Let's try to look a little bit what nature tells us. If I ask nature, what about like charges? Should they repel or should they attract each other? If I have a positive protein and another positive protein, what do we expect to see? Should they just repel each other, or should we see some kind of attraction? What do you think? Huh? You can have both things. Of course, depending on the pH, depending on the salt condition, depending on many things. So what I'm going to show here is two different phenomena. One that's already mentioned, Eduardo also talked about this, ion-ion correlation effect. And the other is what we call charge regulation phenomena. So again, charge regulation can mean different things, but I'm going to talk more about proton fluctuation. That's exactly the name that can be more appropriated. So let's see. If you ask in nature, I mean, the same question that I did here, you can see that in some systems, you can find experimentally, I'm not talking about theoretical data, I'm talking about experiments now, you can find this attraction. This is one of the best examples. You take filaments here of F-actin. In the presence of the monovalent contraions, they repel each other. If I change the valence of the contraions, they start attracting each other. So you can see that the difference between A and B is just the charge of your contraions. And yesterday, I talked a little bit about the electrostatic coupling parameter. And one thing that I described to you is that the valence of the contraions goes to the power 3. When this happens, this number is very much different than 1, you start to have ion-ion correlation effects. So this is the case. Right? Okay, let's continue. In fact, there is a very nice paper at Physics Today where they explain that thanks to ion correlation, you can put inside this capsid all the DNA that you can see as a kind of worm around this capsid here. So just imagine that this material here is highly repulsive, but somehow nature is able to fit all this material inside this small area. It's amazing. And this is, again, due to ion-ion correlation. If you start making more simplified studies, remember this model for polymer that I just showed you. You can use this to quantify ion correlation. So I can put this model, so I just put charges in these M's here, and we put this in the presence of different contraions. In the presence of different contraions, if they are monovalent, if I measure the separation distance, let's just use here this line here, where we have 1 unit of charge per bead. In this case, if they are monovalent, of course, we're going to see an expansion of the chain. But in the presence of divalent, you can see that there is already a reduction. So they start to shrink. And even when we go to trivalent, the size of my polyelectrolyte chain, the end-to-end separations, is smaller than a neutral polymer. So again, another proof, another example of the ion correlation effect. All these results that you can see in theoretical model, people can see on the microscope. So if you have an electronic microscope, you're going to have these snapshots here. And these are just snapshots from the simulation. So you can see that there is a large polymer here, and they start to collapse when you increase the concentration, or not the concentration, they increase the valence of your contraions. So this is something that you can measure in the computer, but of course, I just showed a couple of examples that you can see in experimental life. I showed results using a very crude model, but you can see this also in a more detailed simulation. The difference is the size of your polymer. Here, you can work with big polymers, 300 monomers. Here, you work with a very short peptide, but you can see the same trend. So once you mix it up, a charged object, in the presence of highly charged contraions, you can start seeing this kind of effects. So this is the direction that you probably have to go. Okay? For protein-protein interactions, here is calmodulin, net charge of -24. Here's another calmodulin, -24. So I have -24, -24. Can I expect some attraction? Well, in the presence of monovalent contraions, we see just repulsion. Here is free energy. Remember that I talked about this in my first class, radio distribution function, and from the radio distribution functions, we can get potential of mean force. So potential of mean force as a function of the separation distance here between the center of the molecules. So making this comparison, if this number is positive, it's repulsive. If it's negative, there is an attraction. So change again the valency, -1 to -3, I start to be negative. By the way, I made something wrong. I said -24, actually it's +24. So +24, and the contra ions that are negatively charged. So sorry for the confusion. But anyway, the mechanism is the same. Actually, I made this comment on purpose, because you can see that the charge does not matter if it's positive or negative, as soon as the contra ion has a high valency. Did you get the picture? Cool. Just a cartoon to illustrate it. So you can see that in the presence of the monovalent contra ions, they are far away. If I just increase the valence, they start attracting each other. One simple way to see such things, just imagine that your particle, your macro particle, has a kind of electron cloud. So you can see this as an argon atom. And if you calculate the correlations, if you take the free energy, you can see that this is going to give you an attraction. It's a negative here. So you can do a bit of statistical mechanics that I'm showing as a kind of magic here. But if you work a little bit with this equation, you can end up showing that there is an attraction between these two objects that goes to the power R6. So it's possible to analytically also demonstrate this phenomenon. You have experiments, you have a theoretical development, and you have simulations showing ion-ion correlations. Not only on biological systems, you can see that if you work with cement, cement is a very robust material. And one reason for concrete to be very, very stable is because you also have an ion correlation between the silica particles. So there are some references here where you can check this, and it doesn't matter if you have a biological material or any kind of material, you can see the same physics. You can see like the interaction between highly charged CSH particles in the presence of divalent, so all the time is the valence of the contra ions, is strongly attractive because of ion-ion correlations. So ion correlations are the answers under this regime, where you have a highly charged object in the presence of a highly charged contra ions. Okay, so this is the picture that we have so far. If I try to organize the ideas, we have one regime that we call the Wiki Coupling, when this number here is closer to 0. Another regime where this number goes to numbers bigger than 1. So as much as we are here, we start seeing this kind of weird attraction between like-charged objects. But to be under this regime, remember, I need either to increase the charge of my surface, or I need to work with a high number for the valence of my contra ions. Under this regime, you start seeing this peculiar phenomenon. And if you go to the opposite direction, you just recover the traditional good common sense. Positive and negative are going to attract each other. Positive and positive, like charges, are going to repel each other. That's well described by the so-called de Villiers theory that you also heard about this in previous lectures. Okay? Some snapshots from simulations showing this kind of mechanism. So here we have micelles with a charge around 60. I'm talking about 60 units of elementary charge. In the presence of monovalent contra ions, you can see that they stay apart from each other. In the presence of high valence, they start to aggregate. And eventually, we have a cluster of particles, just changing the valence of the contra ions. So more snapshots showing you the same mechanism. Maybe this can be a good example to deal with coronavirus. We have to decrease the contra ion valence, so people can start to stay apart from each other. Okay. Now I'm going to talk about another phenomenon. And this was even more complex. Lots of experimental data, lots. I'm just picking up a few then here to flash you with this idea. People were observing, as a function of pH, strange things. For instance, here, you see that the Coulomb law is going to predict this dashed line. And they were observing things that were like more attraction in regimes where the molecules, they have the same net charge. You can easily say, well, come on, you just described ion correlation effect, so this should be ion correlation effect again. Yeah, but these calculations, or these experimental data actually, they were happening very close to the isoelectric point, where the surface charge density is closer to 0. And even worse, they were happening in the regime that you have monovalent contra ions. So actually, we were under this Wiki coupling regime. Because if this number goes closer to 0, and this one is closer to 1, this number is closer to 0, so I end up here. So even here, we could observe in the experiments these kind of things. I mean, just plots of it. You can see the charge of the molecules. You can see that the peak here happened, of course, when they were with the same charge. But sometimes we start to see things like, look here, both are negatively charged. Come on. If this is happening in this regime where we have monovalent quantiles and something close to the isoelectric point, it can't be ion correlation. What has happened there? People didn't know. They start talking about complexation on the wrong side of the isoelectric point because you're not expecting to see them. Some of my colleagues, actually I started in this problem because there was a colleague that knocked at my door. And as you know, I work in a pharmaceutical science department. So people, maybe they have, oh, let's see if you're useful for something here. So the guy knocked at my door, hey, I have this experimental data that I don't know how to understand. You work with physical chemistry. Maybe you can help me. Then I look at, wow, I guess your student has done something wrong because they measured this at the very beginning. They measured the complexation between pectin, a polyelectrolyte, with a protein from milk, casein. And they could observe that, just look here, I mean, the red plot is the combination of the two. And the combination of the two happened when they have the same net charge, and even more, the final product was also negatively charged. So for me, at the first moment, your student has done something wrong. Ask your student to redo the experiments. Because you were doing these experiments in monovalent salt concentration. So it's impossible to have ion correlation effects. But they have repeated the experiment many, many times. And then I started looking to the literature, and I found many more other problems similar. So at the end, I had to give up and convince myself that the student was doing something right, and I was doing something wrong. So we started to think about what could be happening there. This is another example about other labs that were doing exactly the same thing. They found the complexation between proteins with polymers in the regime where they have the same net charge, all the time close to the isoelectric point, all the time monovalent salt. I'm just jumping the more and more data. This one might be even interesting to highlight. Just imagine that I have a membrane here. I have a protein here inside. This membrane is negatively charged, and I have another polyelectrolyte that's positively charged. Somehow, this molecule that's positively charged is able to come into the solution and form a complex with something that's also positively charged. Come on, it's hard to believe that this can happen. But people were publishing experimental data of these things. So, come on, I'm able to compete with a negative surface to sequester the molecule being positive and form a complex. There should be a strong interaction happening. I mean, what else could it be? So how can we explain such things? How can we explain that a negative molecule can bind in a negative molecule in conditions that we cannot use ion-ion correlation? So we are not here, we are here, and this does not work any longer. If you look in the literature, you can see that these attractions between like charge, they are very controversial. I took this slide from a guy from France, and you can see that it's really very controversial. And this is very nice because they were even fighting to each other on the papers. They derived, unfortunately, using a wrong method, equations for the potential energy of interaction. So you can see that the attraction of like objects has been under debate for a long time. And of course, this was true for ion-ion correlation effects, and especially for these new, let's call new observations, it was also true. At the very beginning, what people were trying to use as an argument was the so-called patch theory. To simplify the things, just imagine that I have an object that my net charge is plus. It's going to attract another object that has a net charge of plus. So the way that people were trying to convince themselves that it was possible to see an attraction was to imagine that there might be a concentration somewhere in the protein of a patch of opposite charge. So in this example, I could see here a negative surface, concentration of negative charges that in principle could attract this positive thing. And I have built up models to try to prove this. There are simulations like I'm showing here, where you can see here for a protein, the polyelectrolyte chain, a very simplified model as well, and the center of mass of the polymer visiting more the area where you have a pet theory, a pet thing. But the problem is, if you're coming from physics, you know that this is what we would call dipole. So here would be a charge-dipole interaction. And this is not so strong as a charge-charge interaction. So the dependence is not 1 divided by R. It's weaker. And being weaker, how on earth can you have it? Looking careful to this model, they had included in the model also a van der Waals potential. So you can tune your parameter of van der Waals essentially to give it the attraction that you want. And it turns out that this protein, in fact, has also a very high dipole moment. So for proteins like this, it should be perfect, the theory. And so this was the reason that this, in some way, started to be using to explain the phenomenon. But in fact, if you take another protein from the same evolution point of view, like if I take lysozyme, you cannot see such things. So the only way to see attraction is using what I'm going to show next. It's here. This is the paper that I found in the library, so a good advice to students is to spend time in the library. I hope you have done this for the group presentations, because it's there that you find the solution of most of the problems. We were shaking our heads to try to understand what was going on in this system. And Kirkwood, again, the same guy, now you can start understanding why I told you that if his life was longer, we wouldn't have a job, this school would not happen probably, because he has solved many of the problems. And there you can find a paper from '52 where he's able to explain things like I'm showing. When one or both pair of proteins are closer to the isoelectric points, some kind of structure-sensitive electrostatic force starts to play a role. It's in this paper that you have all the equations, the statistical mechanical equations, to prove that there is something called proton fluctuation, that he called at this moment is sensitive electrostatic force. Lucky us, he didn't have access to the protein structure. PDB was not there. So he couldn't do what we do nowadays, go to the PDB, take the structure, and test. We were lucky to be able to do it. He couldn't. But all the math is here. In short, I mean, the paper, what you can see, you can write the free energy for the interaction between the two macromolecules. And you can see that there is a direct Coulombic contribution. So if one molecule is positive and the other is positive, this is also going to be repulsive. But you always have an attraction. You can see the minus sign here, that this is longer range, but this is not too much different. It's R squared the distance here. And this term, being always attracted, depends on a few parameters that you can see here. One is the charge that goes to the power 2, charge square. And then you have this cis. What is this cis? This is the proton fluctuation that you can quantify in a titration plot from the derivative of the charge as a function of pH. So we can take this from experimental data. Or in a simulation, you just take from the fluctuation in charge. If I have a titration model, so my charge can fluctuate through the simulation, I directly get from my simulation these two parameters. So it's okay to get it simple. What you can see from this equation? Well, if I have a protein that has a tendency for high charge fluctuation, a high C number, the C number is going to be multiplied by another number here, that's the charge with the power 2. So as high is the charge that I'm interacting with, and as high is my own probability to exchange a proton, higher would be this number. And eventually this contribution in green can be bigger than the one in red here to beat this contribution. And that's what we have observed. Other things that you can see from here. Just imagine that I have a protein at the isoelectric point. So let's call my protein here A. If my protein is at the isoelectric point, the net charge is 0. So the QA here is going to be 0. This term is going to be 0. This term is going to vanish as well. But I'm all the time left with this contribution. So in this condition that I have 0 charge for my protein, but I'm interacting with something that has a charge, and I have in my protein titratable groups to have a reasonable number for my Cs, I know that I'm still left with an attraction. So as high as this number and as high as the number, higher will be this contribution. Simple like that. So now you start to have clues when you have to think about this phenomena. Because if you are working close to the isoelectric point and you see attraction, it can't be ion correlation. But it can be charge fluctuation, proton fluctuation. Okay? I would jump in the details of the theory. I think you can read in the paper and you can discuss later. I think it's better now that I try to highlight more ideas to you. So we tested it using this kind of very crude model that I was showing you. So this can be good for you to see how useful they are. So using this kind of model that I already showed you, where my polymer, I have this harmonic spring connection, charged object, and the protein, as with the interaction that we already discussed. And here you have free energy, results from the simulation now, free energy as a function of separation distance. And we were very happy to see that in a model that we only have electrostatic interactions, and of course the hard spherical description to avoid the Coulombic collapse. Just back to the equation. No van der Waals interaction, so van der Waals was not important to us. With no van der Waals interaction, we could see attraction. We could measure attraction, and when I compare 3 different protein systems, we can see that the Kirchhoff equation is reasonable. Because just to compare, for instance, here I have the data for lysozyme. Lysozyme has a small dipole moment, which has a reasonable number for the charge regulation parameter, that's the C, the charge fluctuation 1, the proton fluctuation. Then I have here alpha-lactobumin, which has a large dipole moment, and again, some number for the capacitance here, the charge regulation. You can see that in this case, the number increases, the minimum here, between the red and the blue plot. But of course, I have the 2 phenomena together. So this is why I was telling you that when they have done the patch theory, it was good to make a choice for this guy. Okay? Of course, if we go to bigger proteins like beta-lactoglobulin, it's even stronger the attraction because this molecule has a huge number for the charge regulation parameter and also a very big dipole moment. So in this case, we have all the attractions. Okay, we were happy. That was the beginning of the story. In the computer, we can play God, especially in this kind of simplified models. So if I'm working the isoelectric point, I can have a neutral system by different ways. One is to easily make everybody with neutral charge. So I just go to my input file and make all the bits with charge 0. That's one way. We can have the model, the constant-pH model, where the charge can fluctuate and the net charge is also going to be 0. But the charges can vary here. They can be changed during the simulation, but the average number is always going to be 0. I can freeze one configuration here and have a fixed charge distribution. And I can also look in this contribution and just take the first momentum. So I just take the dipole moments. So I forget about quadrupoles and high order moments. And now we can do simulations with the 4 cases, and we can compare. So this is a good way to test what mechanism is playing a role. Remember that in the model, I only have charges. There is no van der Waals. So the only thing that can give me attraction is if something happens with my charge or my charge fluctuation. So let's test lysozyme. You can see that there are 4 plots here. So the uncharged system, that's the neutral one. The non-titrating one, that's the one with the fixed charge. The one with just dipole is the one that you see here, and the one with the titration is the one that I have charge fluctuation. I can only observe attraction if I have charge fluctuation, proton fluctuation. It's impossible to see attraction using the other models for this special molecule that has a weak dipole moment. On the other hand, if my molecule has a higher dipole moment, bless you, has a higher dipole moment, you can see that the dipole contribution and the titration, they are more or less on the top of each other. So again, the patch theory did work because they were really very careful or lucky to select a protein system where both contributions are equivalently good. And in fact, when you have the high order terms, we can see that there is a reduction in the attraction. Okay? So these are, I think, good examples to compare the systems and to show you in a kind of simplified way what can be done. Let's go back to the patch theory. Well, the argument is that these amino acids were responsible for the attraction. Again, in a computer, I just go there, take my input file, make a mutation, and repeat the calculation. We have done mutations for individual contributions, so one by one, and for all the 5s. We can remove them, and we can still see attraction. So the patch theory for this protein does not make that sense. Because if you have charge regulation, charge fluctuation, you can still see this. You probably have notes that I'm using all the time, charge regulation, charge fluctuation. I'm using both names to try to clarify that what I mean by charge regulation is proton fluctuation, just to avoid confusion between the different names that are used in the literature. Well, we have tested this for many proteins, so I think I can skip, but you can see that for all the systems we can find a complexation. Maybe it's good to just point out that proteins like BSEA, albumin, they are proteins that like to stick to anything. You can see that it has a very strong attraction with polyelectrolytes, for instance. So this molecule is used a lot in experimental studies. Leandro mentioned a little bit about this, that has a very strong attraction. And it's easy to see that it's a protein that like to form a complex to anybody. And the simple reason is it has a high dipole moment and a high charge fluctuation parameter. Well, I jumped these slides, just comparison between things. I think I read it, maybe this one is like kind of, I can summarize here. For instance, here we have the radial distribution functions multiplied by R squared to amplify the results. And in just one slide, we can show you the 3 mechanisms. And also, I can highlight one detail that usually people don't get properly when you just see the equations. When you are in the repulsive regime, you can see that the 2 molecules are apart to each other. So you're going to see that there's a tendency to have something really far away. If they are attracted, if they are forming a complex, you have a high peak. So you can see that these are the 2 streams and the 2, let's say, common sense situations. When we are talking about this kind of phenomena, we don't have something so strong as this one. So this is a snapshot of the simulation. You can see that there is some kind of transition. So part of your molecule is strongly connected to the protein, but you have something floating around. Of course, this varies between the charge of the molecule, the condition that you are studying, but I think this is good to represent what sometimes you are observing. It's an attraction, but it's not that strong as a traditional Coulomb attraction. It's good to have this in mind. So if you put salt on the system, this is going to be released easily. This one is going to be a little bit harder. Okay? Let me see. You can look also to the properties like radius of gyration, end-to-end, so you can monitor the behavior of the system. Of course, when they are apart to each other, they behave as ordinary polyelectrolytes, free in solution. So this is the dashed line that you have here. When they are under complexation, you can see that they are going to be closer, smaller. Anyway, I think it's okay. Like when they're in the repulsive regimes, you can see that they recover essentially this situation that I just described, like isolate polymers. And when they are complex, you see that these numbers are going to be smaller. And this is true for all the proteins. Another thing that we have done to test the patch theory against or together with, in a kind of comparison, maybe it's better, a comparison with the charge fluctuation, was to observe where we have changes in the protein, which amino acids were taking part in these things. When I measure the radial distribution function, I have averaged everything, and we are essentially looking to the separation G. So orientations, they are averaged out together. And our question was, okay, if we have all these mechanisms together, do you see that we have a specific area of my protein surface that's going to be affected by the presence of the other charged molecule? Or they can bind anywhere? In other words, do I have a specific interaction or a non-specific colloidal interaction? If the patch theory is true, we are expecting to see a very specific interaction in a given part of the protein structure. If it's non-specific, we are supposed to see changes all over the protein surface. So remember that the pH affects there's this kind of neighboring effect. Well, if I have titrable groups all over my hand here, and this object here is a charge. When I approach these two different tetraber groups, I'm going to shift their pKa's. So this is a way to map what's happening in the surface using basic physical chemistry. I simply have to put my probe around different points, and I can measure what happened with the tetraber groups. So if they were affected by the presence of the charge, it means that this charge was closer to them, because if I put them apart, there is no effect. So during the simulation, we already have the data. We already are recording the charges, because I needed this information to do the titration scheme anyway. So mapping the pKa shifts all over the surface for systems like, in this case, is alpha-lac, you can see that there are charges, there are changes all over the protein surface. So again, we don't see any specific interaction. The polymer has been visiting all the protein surface. By the way, this idea to use the pKa shifts is what you probably have been seeing in the poster that Sergio was presenting. We are using the same concept. The concept that was born in this paper is the same concept that we are using to predict epitopes in protein virus, okay, in viral proteins. So the proceed pKa method is based on this idea. Again, basic things can be applied to more complex systems for practical reasons. I'm not going to have time to show you the results, but we have done also for the coronavirus. So, and we can use this to compare what happened with the previous SARS infection and what's happening with these ones. And I can anticipate the data to you that the epitopes, they are not the same. They are equivalent, but we have some difference. And the news that's not good is that the antibodies that were working with the previous SARS infection do not work with this version of the virus. So but at least we can come up with some ideas what kind of changes we have to do in the antibodies to make them more efficient. So this might be some contribution that we can give in this business. Hope soon. Okay, I showed data about protein, polyelectrolyte, protein-protein interaction. I could continue and show about protein-RNA interaction. We can go again and have this discussion about charge fluctuation, these kind of things. I have more examples, but I think my time is about to be finished, so I'm going probably just to jump directly. You see, there were much more things, but I think I can jump directly to the main conclusions here that are like take-home message from all my 3 talks. So the first thing is that I hope I could convince you that very often simplified models are a good way for you to rationalize complex systems. So what we learn in physics is still valid. Of course, you can go to more detailed simulation, you can learn things, but very often simplified mechanisms, simplified models can really help you to understand complex things. They can be used to design rational applications. If you can understand how is the connection between your mutations. Yesterday, I make this comment here, and this is still valid for this contest. If I do a mutation and I see that I increase my binding affinity, I know that this mutation is going to be help me. And this is the idea that's behind what I just mentioned about the development of new antibodies. So if you were able to predict what kind of a mutation I can do to improve my binding affinity, I'm providing some evidence or some ideas that someone can go to the lab and try that mutation and hopefully it's going to work. Okay? I showed the result that electrostatic selectivity is really possible and it's present. And also, charge fluctuation is a mechanism that's important. So if you're not doing, for instance, constant pH simulations, everything that I said in the last 15 minutes about charge fluctuation is not going to be incorporated in your model. So if you'd like to make a model that describes pH effects and you take out one important phenomena, you don't have the whole picture. Maybe you can end up in some result that can be closer, but very likely you're not going to see what you would like to observe. So be careful, depending on the regime that you are working, depending on the conditions, the both phenomena that I mentioned, ion correlation and the proton fluctuation, they might be important. I jumped it very quickly, but this might be something that could be maybe a good way to summarize it. Here I have, for instance, the interaction between a peptide and a membrane, a model for a membrane. You have the experimental data. If you do fixed charge simulation, you can see that your result is very much different from the experimental one. Of course, we are comparing salt effect here. Only when I incorporate charge fluctuation in my model that I can come up with results that are closer to the experimental data. So this is really what I meant when I wrote here that charge fluctuation is a key parameter. So depending on the system, this is the take-home message, depending on the system, you have to do constant pH simulation. And you have to make sure that you have reached convergency. Otherwise, you also have troubles. Hope you're not like that. I think I really have to congratulate you to be brave enough to come in for this last talk in the last minute before you have your presentation. I think it's really tough for the students. We apologize, but you know, there are constraints that we also have to follow. But I really would like to congratulate you, and maybe deserve my time to clap you. I showed data from different projects. I just try to pinpoint things that I think could be useful to create a historical presentation where you could see different aspects that I believe they are important for someone that would like to start or already work in this business. There were different people. I'm not going to read all the names, but of course, I have to say a very special thanks to the founding agents and institutions that provide money for different things that are involved here, including a Swedish place that provide one of my collaborators access to computers that I can still use to run the calculations. And I guess that's my final phrase before you can make any questions, and we can have maybe 20 minutes of coffee break. That's it. Questions? Yes. Maybe you can use the microphone. I don't know if I'm getting tired or getting even more older the last days, but I'm not here any longer. Aperta o botão. Press the button.
Okay. Thank you for this nice lecture. Just for clarifying, when you say repulsion, you mean there is no interaction at all, or they should separate into different phases?
Well, by repulsion, I mean that they are repelling each other, that's all. There is like if you have a +5 and a +5, they are going to repel each other. You can have phase separation, you can have other things, but at the very beginning, eventually the repulsion is not that critical for them to be really apart from each other that you can have a phase separation. But one could be very weak that they just stay a little bit apart from each other. Maybe they are able to stay in the same place, but keeping the 1 meter separation distance, something like that.
Thank you.
All right, you're welcome. Any more question? Otherwise, Rolf, what do you think? 20 minutes of a break?
Yeah, at least.
Okay, so 20 minutes of a break, and then we come back for your turn. So now I pass the word to you to finish the show. So thank you.